Hi, in this video, I'll present our work on learning multiple probabilistic degradation generators for unsupervised real-world image superresolution. The goal of the unsupervised real-world superresolution, or USR, is to reverse the degradation process, which is unknown and only implicitly represented through the corrupted observations. To restore the high-resolution images from the observations, one typically needs to learn the degradation model and train the upsampling neural network to revert it. Therefore, the performance of USR models largely depends on the quality of the degradation models. In the real world, we only have access to the unpaired dataset that consists of the set of high-quality images and the separate set of low-quality images. To learn the flexible degradation model, conditional GANs are widely used as they can be trained on the unpaired dataset using cycle consistency. However, previous approaches ignore the fact that the degradation process can be stochastic in the real world. In other words, for a given high-resolution image Y, there can be multiple corresponding low-resolution observations X obtained from the same degradation process. Since deterministic degradation models fail to capture the complex distribution of low-resolution images given an high-resolution imaging, the performance of the upsampling network is suboptimal. To settle the issue, we train a probabilistic degradation generator. To make the degradation generator probabilistic, we introduce the hierarchical latent variables to the previous conditional GAN model. This can be easily implemented by injecting the Gaussian noise with learned covariance into the intermediate feature maps of the degradation generator. In fact, we set the variances of latent variables to the free learnable parameters shared within the spatial dimension. This is equivalent to the noise injection module introduced in the StyleGAN paper, and we believe that this is one of the reasons for the improved synthesis quality of the low-resolution images. Since we trained the probabilistic degradation generator using GAN laws, our method is also prone to mode collapse. Even though complicated techniques can be used to alleviate the issue, here we propose a simple solution. To train multiple degradation generators, but with different architecture. After multiple degradation generators are trained, we can train an upsampling network using the pseudo pairs synthesized by degradation generators. Although this approach works, we further propose to train multiple upsampling networks with collaborative learning for the ease of training. Specifically, we assign the upsampling networks to each degradation generator, where the upsampling network is trained to revert each degradation model. Furthermore, each upsampling network distills its knowledge to other models, facilitating the training procedure. As shown in this figure, our probabilistic generator can synthesize diverse low-resolution samples given a high-resolution image. We further compare the probabilistic degradation generator to the deterministic degradation generator on the validation set of the entire 2020 dataset, where high-resolution and low-resolution pairs exist. This figure shows that the probabilistic degradation generator achieves lower LPIPS than the deterministic version, indicating that the probabilistic generator estimates the degradation process more precisely. Moreover, we compare the performance of upsampling networks trained to revert the deterministic and probabilistic degradation generator. As shown in the table, the upsampling network trained with the probabilistic degradation generator achieves higher PSNR and SSIM value. Here, we investigate the effects of using multiple degradation generators and training them with collaborative learning. The table shows that using a single degradation generator leads to the lowest PSNR value. Moreover, collaborative learning achieves higher PSNR than a naive combination setting, where a single SR network is trained to revert the multiple degradation generators. As shown in the figure on the right side, the PSNR increases smoothly with collaborative learning, as indicated by the red color. Contrarily, the training collapses without collaborative learning, as indicated by the blue color. Our method achieves state-of-the-art performance on the benchmark datasets, both qualitatively and quantitatively. In this figure, we analyze the generalization ability of different SR methods. Specifically, we inject additive Gaussian noise into input images at test time and see how each model adapts to the out-of-distribution samples. As shown in the figure, the performances of existing methods are drastically degraded by input perturbation, limiting the practical use of SR in the real world. In contrast, our model preserves the performance even when the perturbation gets stronger, since our model is trained to adapt to the diverse pseudo-pair data generated by multiple probabilistic degradation generators. In summary, we propose to train the probabilistic degradation generator to better approximate the degradation process, which is often stochastic in the real world. Furthermore, we train multiple such generators with different model architectures to increase the mode coverage. Lastly, we showed that upsampling networks can be effectively learned with the collaborative learning strategy. Thank you for listening, and we encourage you to check out our code.